Hi, this is Professor Jamei Chen at California State University, Long Beach. In this video lesson today, we'll look at properties of quadratic functions. A quadratic function is a polynomial function of degree 2, that is, n equals 2 in expression of a polynomial function, which takes in the form of ax squared equals bx plus c. A is not equal to 0. Require that a is not equal to 0 to make sure we actually have a quadratic function. Imagine if a being equal to 0, then we simply just have bx plus c, and that would be called a linear function. Its graph corresponds to a parabola, which is used in many situations in real life. And I'm not lying when I say that it appears in many places in real life. A quick Google search by typing in images of parabola in real life, you can see that it actually shows up in many places that you might encounter. For example, Eiffel Tower, roller coaster ride, McDonald's, basketball court, the Golden Gate Bridge, arches under the bridge, and the trajectory of which a whale or a dolphin jumps, video games, and even bananas. So knowing the functions and the behaviors of parabolas helps us to actually model a lot of the physical objects in the real world. For a computer scientist who writes computer programs, especially 2D computer programs, they need to know how to model a lot of the trajectories, the jump trajectories or movements using these curves. And one of the curves that is popular apparently from what we have seen here is the parabola curve. Okay, so you need to know very well of what each component of the parabola means, and in order to graph a quadratic function, we need information about the vertex, which is the lowest point or the highest point on the graph, and the way it opens, and typically is up or down. We can get all of those information once we convert a quadratic function into what we call the standard form. And a strategy to do that is to do it by completing the square here. So we're going to illustrate how we convert a given quadratic function into its standard form by completing the square. Next, start with the function f of x, which is ax squared plus bx plus c. The first step is to factor out this coefficient of a, and a is called the leading coefficient for the problem here. If you factor out the a only from the first two terms, the terms that involves x squared and x, and leaving the constant c outside of it, we will get x squared plus something here times x. Now, to get this, we look at what we want to get back at the end. So you want to take a and multiply by something here to get back to b. Well, certainly b has to come back, but then I don't want to see a at all, so I need to divide it back here. And again, c is outside of this factoring problem. Then next, we're going to complete the square on this inside bracket here. We ask ourselves the question, what do I need to add to the current expression here in order for this entire expression inside as a complete square? What a complete square means, I can write it as x plus or minus some number, the whole thing squared. Now I put plus here because this is a plus problem here. If this was a minus, then I will actually change this to a minus problem. Okay, alright, so then how do I actually figure out what number to add? Well, the strategy is very, very simple. All you need to do is take your current middle term here, which is the b over a, divide it by 2 and square that. Okay, so it's just going to do b over a divided by 2, which makes it a 2a down here, and the entire thing squared. If you do that, then it's just going to be b over 2a inside here. Don't forget, this is the term that we actually added to the entire problem. So to balance out, we need to subtract it back. So we're not changing the equation. So here we have plus c from the original problem. And we're going to subtract what we added. How much do we actually add it here? We actually added a times b over 2a quantity squared. So it's going to be a times b squared over 4a squared, because I basically just squared the quantity b over 2a in one step. So altogether we have a times quantity x plus b over 2a quantity squared plus the overall constant term from there. Here we notice that a can actually be cancelled with one of the a's in the denominator, so we have c minus b squared over 4a. That's the constant term. Alright, so doing mathematics is not about pushing numbers around, and now that we've gotten this new form, what we call the standard form, let's try to understand what this standard form is telling us. Notice that this term right here is free of x. It doesn't have any x involved, which means that it doesn't matter what x value I put into this entire thing, it doesn't change the value over there. Okay, that's out of our control. And on the other hand, so what we know about this first portion right here is that it's the squaring of this entire quantity. And then we know that whenever we square a negative number, we always produce a non-negative quantity. So if this thing was 0 and you square it, you will get 0. If this thing was positive or negative and you square it, it will produce a positive quantity. So this portion is always going to be positive or 0. So really what's affecting this whole equation is this value of a. Because if a is positive, actually would make this entire first part positive, because you have a positive number times a positive number, then you actually get positive. And if a is negative, then this entire first set of quantity would be a negative quantity, assuming that you actually don't have a 0. Okay, so we're going to look at what a actually does to the quadratic equation very closely next. So I want you to notice that if we were to plug in x equals negative b over 2a in this first term, this entire term actually goes to 0. And if that's the case, this is already equal to 0, so you can ignore it. Let's look at what happens to the second quantity here. If a is greater than 0 in this case, then the quantity c minus b squared over 4a would then produce a positive quantity here and a positive quantity there. Now we're looking at c minus a positive quantity here. But it's going to be the smallest it can possibly be for this function. Therefore, the function f attains a local minimum at the point x equals negative b over 2a. On the other hand, if a is less than 0, then the quantity c minus b squared over 4a would then have positive quantity on top, but now we have a negative quantity on the bottom. So we're looking at c minus a negative quantity overall, because positive divided by negative would produce a negative quantity. If you're minus a negative quantity here, it actually produces a bigger quantity than c, which is what you started with. So this actually is the largest the function value can ever be. Hence, f attains a maximum at the point x equals negative b over 2a. So to summarize, we know that a is going to be greater than 0. Then we know that the function must have a minimum point at x equals negative b over 2a. And if we have a is less than 0, then that means the function is going to have a local maximum at the same point. It turns out this point, x equals negative b over 2a, is called the vertex point of that parabola. Furthermore, if f has a minimum, then it must look like, right? Because if it had a minimum, that means it's gotta open up. So what this means is that every time we have a greater than 0, its parabola has to have a local minimum. If it has a local minimum, that means it opens up. So right away we can associate this a being greater than 0, indicating that the parabola is going to open upward. On the other hand, if f has a maximum, then its picture must look like this. If its picture looks like that, that means the parabola must open down. So right away we know that if we have a value being a negative to start with, then it's got to have a local maximum, which indicates that the parabola opens downward. Well, in either case, the lowest point or the highest point is called the vertex, which has the standard form negative b over 2a comma f of negative b over 2a. This is just the y value of this function evaluated as the x value of the vertex. For simplicity's sake, you'll most likely see the standard form written as f of x equals a times x minus h quantity squared plus k, where this h is the x-coordinate of the vertex, negative b over 2a, and this k is essentially the function evaluated at the vertex, negative b over 2a, or as we saw earlier in the complete square form, it was given by c minus b squared over 4a. We rarely actually remember this formula here. We simply just evaluate our vertex using the function given us. And this coordinate h comma k is called the vertex. Let's look at a couple of examples next. Consider the functions f of x equals 5x squared minus 30x plus 49, and the second one is the negative 4x squared minus 12x plus 1. I want you to pay attention to the fact that one of them has a positive leading coefficient and the other one has a negative leading coefficient. We wanted to contrast the difference between those two. So the first step is to put the function in a standard form, and I'm going to do that by completing the square. And we're going to sketch the graph of the function f. And notice the word sketch. We don't need a detailed graph of this. We just need to know the lowest point or the highest point, which is the vertex, and whether or not that the parabola opens upward or downward, and also maybe a couple more points to help us sketch the shape of the graph better. And eventually wanted to figure out whether the function has a minimum or maximum depending on the leading coefficient value. Alright, so let's start with the first one here. We're going to complete a square on this one. Factoring out the 5 out of the first two terms, so we have x squared minus 6x. We need to figure out what number to add here to make it into a complete square, and I still have the constant plus 49 on the outside. The number we're going to add is half of negative 6 and then square it. Half of negative 6 is negative 3, and if we square that we get a positive 9. So I'm going to add 9 here. If I add 9 there, that means we actually added 5 times 9 in reality. So we need to subtract back 5 times 9, which is 45. So now this quantity turns into a complete square where I have x minus half of this term, which is just 3. And the whole thing squared. Again, this negative is because it is a negative sign in the original problem. And the constant term is 49 minus 45, which gives us 4. Now this result is called the standard form. As you put the function in standard form, you want to immediately notice where the vertex is. And so simply just read off the vertex. That's going to be this value here, comma, this value there. Figure out the x-coordinate of the vertex. You basically ask yourself the questions, what value of x you put into this quantity here to make this thing 0. And it should be obvious that it has to be 3. Now if this entire quantity is equal to 0, then you're left with the value of 4 for the y. Okay, so that's why the vertex is simply just 3, 4. And we also notice that because the leading coefficient is a positive quantity, and that's the a value, remember, since the a value is positive, that means we actually have a parabola that opens upward. So in my mind, I've already kind of generated this picture. I'm just simply just find my vertex point 3, 4, and I know it's going to look like this because it's going to open upwards. The question is, which point or how wide or narrow this parabola really needs to be depends on what other points this parabola actually goes through. In order actually to have a more sufficient sketch, I need to figure out a couple more points. And typically, the points that are helpful to get are the x and the y-intercepts. So for example, let's try to figure out the x-intercept. Well, the x-intercept is when the y value is equal to 0. So you look at your original expression here in the standard form, you ask yourself the question, what can x value be in order to get y equal to 0? So that is to say 0 equals 5 times x minus 3 squared plus 4. Could this actually be possible? Can you actually stick in any x value there to make this equation true? Well, the answer is no, because like we analyzed this before, this quantity will always be non-negative. Right? The smallest this thing can possibly be is 0 because of the squaring. If 0 is the smallest this thing can be, and we have to add 4 to it, this will always be greater than or equal to 4, regardless what x value you pick, which means that this equation of 0 equals 4 would never be true. And that means that we actually don't have any x-intercept. On the other hand, to figure out the y-intercept, we need to set x equal to 0. So in that equation, if we set x equal to 0, we would get 5 times 0 minus 3 squared plus 4. Well, that is equal to 49. So that means the y-intercept is at 0, 49. Now we have a better idea of what the graph of this thing looks like. So I'm going to go and label my vertex, which is at 3, 4, right there. I know it's going to open up. I know it's going to intersect the y-axis at 49. So I'm just going to say out of the scale, I'm just going to label that as 49 because it's a little bit too big for what I've drew here. So I'm going to say this graph needs to go through that point because it's going to open up, and it's need to actually be a mirror image of what appears on the left and then on the right. So it needs to look like that. And it's very obvious that this graph actually does not intersect the x-axis at all, which makes sense when we did the analysis there. We couldn't find x-intercept. So now to answer part C, whether or not we actually have a minimum or maximum, it should be obvious now. Because a value is greater than 0, we must have a minimum value, which appears at f of 3. Right, so the minimum value really is the y, basically the y value when you evaluate the vertex at. So when you evaluate this as 3, you simply just get the y value of 4. So we would say that the parabola or the quadratic function attains a minimum value at x equals 3 with the value of 4. So you can write it as f attains a minimum value of f over 3, which is really the k value in the standard form, and that turns out to be 4 at x equals 3. You should now go ahead and then pause the video and try to do number 2 yourself and come back for answer. So to start with this problem here, we're going to factor out the negative 4 from the first two terms here. So we have x squared plus 3x, and I need to figure out what number to add here. Well, it's going to be half of 3, and then square that. And I have my constant term of plus 1. Well, let's figure out what I need to do to compensate what I've just done there. I actually added 9 over 4 multiplied by the negative 4 there. So really I did minus 4 times 9 over 4. The 4's cancel. I really just added a negative 9. So if I add a negative 9, which means I subtracted 9, I need to add 9 back. Okay? So then now I have a minus 4 times the quantity x plus half of 3, the whole thing squared, plus 10. This tells me my vertex is at, remember the x value that will make this quantity 0. Well, that's going to be negative 3 halves. And if this entire quantity is equal to 0, then your y value is just going to be 10. So my vertex is at negative 3 halves comma 10. And notice that the a value here is negative. That means the parabola should open downward. So I already have a good mental picture of what this looks like, but I need to figure out a couple more points to graph my parabola a little bit more intelligently. So let's do the x-intercept first. For x-intercept, I need to set my y value equal to 0. So that means I need to solve the equation negative 4 times x minus 3 halves quantity squared plus 10 equals 0. Okay, and then this is a quadratic equation. So my strategy here is to actually isolate this guy here. Alright, so I'm just going to move the 10, actually move this entire quantity here to the right hand side to turn this into a positive thing. So I have 10 is equal to 4 times x plus 3 halves squared. And I'm going to divide it by 4 both sides to get rid of this coefficient. So I have 5 over 2 equals x plus 3 halves squared. Now I notice that if I just take square root both sides, I can get rid of the square on the right. But remember, when you take square root, you always get plus or minus as the result of that, as in any quadratic function it should have 2 roots. So if I do that, I get square root of 5 over 2 plus or minus equals x plus 3 halves. And the square root is the opposite operation to squaring, so that successfully gets rid of the squared. Alright, so the only thing left to isolate x on the right hand side is to subtract 3 halves both sides. So that means I have my x value to be negative 3 halves plus or minus square root of 5 over 2. What this tells you is that there are actually 2 x-intercepts. One is obtained by taking the positive root, and one is obtained by taking the negative root. For the y-intercept, it's a lot simpler than that. If we simply just set x value equal to 0, I will get y equals a negative 4 times the quantity is 3 halves squared and plus 10. And that is just going to be negative 4 times 9 over 4 times 10, which gives me negative 9 plus 10, and that is equal to 1. So now I'm going to use all the information I've gathered here. The vertex is going to be a highest point because notice that the coefficient, the leading coefficient here, is negative, right? So it's going to open downwards. I know that vertex is going to give me a maximum point. So I'm going to find my negative 3/2 comma 10. I'm just going to say right about there, okay? And it's going to go downwards. And as you go down, it's going to cross a few points on the way. That'll be the y-intercept, which is at 1. So I know it's going to go through this point 1 here somewhere on the y-axis. And for the x-axis, it's going to cross 2 points given by these two values. I'm a little lazy to actually figure out what that is, but I just know that one of them is going to be on the left of the vertex and the other one's going to be on the right of the vertex. So eventually the graph should look like this, where if I just clearly label the points of this graph intersects, then I would be okay. So if this first point of intersection on the x-axis would be negative 3/2 minus the square root of 5/2. And the one on the right is going to be negative 3/2 plus the square root of 5/2. I know it's to use the negative, the left-hand side, because points are to the left on the real number line is actually smaller than the points on the right of it. So I know the subtraction will accomplish this task for me. And this point on the y-axis is going to be 1. And the vertex here is going to be at negative 3/2 comma 10. This will be a perfectly good sketch of a parabola, and that's all we're looking for here. For part C, because we have a downward-facing parabola, we know that we're going to have a maximum value at 10. And you can actually just get that from looking at the graph. The maximum value is the y value from this, which is also the y value or the y coordinate from your vertex.